Please take a look at this PDF file. I'm also gonna share it with you on WhatsApp. I think I'm gonna share the link for these files. We're gonna use this as our learning material in the nearest future. And these files are pretty well organized, so it's good supportive material for us. And up till now, we learned about most important characteristics of polynomial functions, transformations of polynomial functions that we can perform. But there is one more thing that we have to discover before starting the rational functions. Basically, the rational function is the combination of two polynomial functions, f of x. For example, f of x so for example, f of x would be a rational function. If it will be represented in the form of fraction, whereas, for example, g of x over, I don't know, for example, p of x, two different functions that are both polynomials, numerator as well as denominator. Okay. And what basically happening to the function, in order to understand that, we have to first understand what reciprocal of linear function is. We're gonna start with the basics. So we're going to use following example for our discussions today. F of x equals 2 over x minus 3. 2 over x minus 3. Okay? So a rational function is the result of division of a polynomial by another polynomial. It's pretty similar to a rational number like 7 over 8. But imagine if instead of numbers, 7 and 8, we have polynomial functions or polynomial expressions like x squared plus x plus 5 divided by x squared plus x plus 5. There is an important thing to remember as well, that for rational function, the denominator can't be 0. So bottom part cannot be equal to 0 because we cannot divide by 0. Just accept it as it is. It is pretty complicated mathematical question to explain, and you don't really need to know that right now. Just accept the fact that denominator cannot be equal to 0. So in our example, f of x equals 2 over x minus 3. X minus 3 does not equals 0, which means x does not equals 3. This is like a basic rule for rational functions. Denominator cannot be equal to 0. Later on, we're going to discuss what happens when x approaches this value of 3 or some other value that gives us 0. Next, part is the values of independent variable that makes the denominator 0 are excluded from the domain. That's what I just discussed. They are not included in the domain of a function if, with respect to this value, function equals 0. In example, our function that we're using as an example right here, f of x equals 2 over x minus 3. The domain of this function does not exist at x equals 3. It's called a restriction. Basically, we apply certain restrictions on our domain. Therefore, domain of the above rational function, reciprocal of a linear function, is x belongs to all rational numbers. At the same time, x does not equals 3. So if we were like to plot every point of x that included like 1, 2, 3, 3 would not be included. It would be like empty dot. It won't be included into our domain. The graph of the function approaches the vertical line passing through the restricted value of independent variable is called what? The graph of the function approaches the vertical line passing through the restricted value. So for example, our graph has excluded point when x equals 3. Let's sketch a line. And let's say our graph would approach it something like this, but it would never cross it. So the graph of the function approaches the vertical line. This is the vertical line that passes through x equals 3, which is passing through the restricted value of independent variable, is called asymptote. It's basically asymptote. When independent variable approaches 0, the graph approaches this line. It's not pretty accurate. It should say when denominator approaches 0, the graph approaches this line. So for example, the closer we get to value of x equals 3, the closer the graph would get to this vertical line. Is there any questions up till now? No questions, it's good. But please feel free to ask any question if you don't understand something. So moving on, the graph of the function approaches the horizontal line, but never touches such line. So this line is called asymptote, vertical asymptote. Oh, sorry, we're talking about the horizontal line. This happens when independent variable approaches positive or negative infinity. The graph approaches this horizontal line, basically some stable value. If we look into our example, and let's say, what would happen if x travels to positive infinity? If x travels to positive infinity, incredibly big positive number, it means that we divide 2 by incredibly big positive number, which gives us number incredibly close to 0. So our graph would look like this. This horizontal line would be y equals 0. It will pass through the beginning of the coordinate axis. You see? This is our horizontal asymptote. So vertical line that the graph is not touching but approaches is a vertical asymptote. Okay, and the line that is horizontal and the graph also is not touching it is called horizontal asymptote. Once more, when independent variable approaches positive or negative infinity, the graph approaches the horizontal line. What would happen if x travels to negative infinity? If x travels to negative infinity, we're going to see that we divide 2 by incredibly big negative number, which means it will approach it will approach 0 but from the other side. So the graph would look like this. One line to the right hand side, the other line to the left hand side from this vertical asymptote, right? And our horizontal asymptote, it remains the same when y equals 0. X-intercepts of irrational functions are the values of independent variable when numerator becomes 0. For this particular example, there is no such number that would give us numerator equal to 0, or will give us function equal to 0 at all, which means this example has no zeros. So we have no x-intercepts. Vertical asymptote can be found by finding the independent variable that makes the denominator of rational function 0. One more time. Vertical asymptote can be found by finding the independent variables that makes the denominator of rational function 0. Vertical asymptote from top to bottom can be found by making denominator x minus 3 equal to 0. In our particular case, it's x equals 3. Vertical asymptote can be found by finding the independent variables that, this we already covered. When independent variable is approaching infinity, the graph approaches the horizontal asymptote. When independent variable is approaching infinity, the graph approaches the horizontal asymptote. This is we already discussed. So next part of our class, if you don't have any questions, solving or sketching the graph of any rational function. How will we do it? It's pretty much similar to what you did with any other function. First, you should find the domain and range of such function. For our example, domain is all x, e, r, except of x does not equals 3. Range for this function, as you can see, would be all the way from positive infinity to negative infinity. So all rational numbers for y. We also should find x and y intercepts. In order to do that, we should put numerator equal to 0 and find x intercepts. As I've spoken before, in our example, there is no such x-intercepts because numerator is always positive. Also the range, this is important part. Domain is restricted by the vertical asymptote, while the range restricted by horizontal asymptote. In this particular example, horizontal asymptote is y equals 0, so y does not equal 0 at all, as well as x does not equal 3 at all. we should find horizontal, vertical, and oblique asymptotes if they exist. Horizontal and vertical asymptotes are fairly easy to find. Horizontal asymptotes, you just say x travels to plus or minus infinity. And vertical asymptotes, you just say when denominator x minus 3 or in any other case equals 0 and denominator equals 0. So how to approach x to positive and negative infinity? Just imagine that instead of x, you substitute some incredibly big positive number or incredibly big negative number and see what value does it tends to approach. For example, if you start increasing it gradually, like starting with -10, then -100, then -1000, and you go all the way up for something like -1,000,000, you're gonna see that eventually your function tends to turn into 0. But it would not be exactly 0. It would be some very small negative number or very small positive number. In other case, you could have any other horizontal asymptote. It's all uh, basically depends on particular example. So looking into our example, we already know how to find the domain and range, x-intercepts and y-intercepts. How to find y-intercepts? Basically, you set x equals 0, right? When x equals 0, we see that 2 over -3 would be our y-intercept. Vertical asymptote x equals 3, horizontal asymptote y equals 0. Because this is the x value that makes the denominator 0, this value of x is the root of original linear function. Because function never becomes 0, more discussion on how to find horizontal asymptote will be in the class. Yes. So horizontal asymptote, as I've said, basically approach x to plus and minus infinity and see what value do you get. It's not so overcomplicated. So graphically, you have to identify x and y-intercept, horizontal and vertical asymptotes. For example, we found y-intercept, it would be 2 over -3, point somewhere here. We found that there is none x-intercepts, none of them. And we also know that we have vertical asymptote at x equals 3 and horizontal asymptote at y equals 0. Now, we know the end behavior, right? On both ends, it will be close to 0, right? Meanwhile, around the vertical asymptote, it will travel either to positive or negative infinity in y-axis around the vertical asymptote. That's how it's going to be most of the times. How can you do it? You can substitute x, some number close to 3 from left and from right-hand side. For example, from left-hand side, I would substitute 2.9 instead of 3, and I'll see that it function travels to negative infinity. On the right-hand side, I would substitute 3.1 and see that function tends to travel to positive infinity on this end. Any questions so far? Good. So let me clean the drawing. So what you have to remember, the graph of the reciprocal of linear function is approaching infinity if the linear function is approaching 0. And if the linear function is approaching infinity, then this reciprocal will be approaching 0. Okay? One more time. The graph of the reciprocal of a linear function is approaching infinity if the linear function is approaching 0. And if the linear function is approaching infinity, then its reciprocal will be approaching 0. For example, we are gonna consider a function f of x equals 1 over 2x minus 1. Domain of this function would be such as x, rational numbers, excluding x does not equals 2 case when denominator equals 0. So 2x minus 1 does not equal 0. 2x does not equals 1. X does not equals 1 over 2. Does everybody understand how I did these steps? So x does not equals 1 over 2. Range of such function would be respective. So y, e, r. But now we have to check for horizontal asymptotes. When x travels to negative infinity, what would happen? We would have incredibly small negative number. Positive infinity, incredibly small positive number. So our horizontal asymptotes, when basically numerator never equals 0, so y does not equals 0 is our horizontal asymptote. This is about the domain and range. Describe the behavior of the function near the vertical asymptote. So near the vertical asymptote, in order to do that, we know that our vertical asymptote appears at x 1 over 2. So we're going to take some value to the left-hand side from 1 over 2 and to the right-hand side from 1 over 2. To the left-hand side, we're going to take 1.1 over 2. And to the right-hand side, we're going to take, oh, sorry, this is to the right-hand side. So to the left-hand side, we will take 0.9 over 2. The right-hand side will take 1.1 over 2. Okay, now you can substitute these values into the given function and see what happens. That's how we describe the end behavior around vertical asymptote. But I'm telling you, in most scenarios, one side would give you positive infinity and the other one negative infinity. When you take 0.9 over 2, we're going to get 0.9 minus 1. 0.9 minus 1 gives us negative 0.1. So when we divide 1 by some negative small negative number, we're going to get negative infinity. So here we have negative infinity to the left-hand side from the vertical asymptote. To the right-hand side, we obviously going to have positive infinity because we divide 1 by small positive number. If we were to sketch this graph, let's start by giving us some coordinate axes. We know we have vertical asymptote at 1 over 2. And we have horizontal asymptote at y equals 0. And we know to the left-hand side, it travels to negative infinity. To the right-hand side from this value, it travels to positive infinity, right? Now we have to describe the end behavior. This is how we do basically find the horizontal asymptote. Set x travels to positive or negative infinity. And we already figured out that if we approach x to positive infinity, we're gonna have incredibly small positive number. So here, somewhere here, incredibly small positive number close to the horizontal asymptote, right? And if we travel to negative infinity, we're gonna get incredibly small negative number of y. So it will be here. Combining all of that information, that here is to this side from the vertical asymptote, here it's to this side from vertical asymptote. And now the last step for you is sketch a graph of this function. We also can see that there is no x-intercepts because function never equals to 0. And there is y-intercept when x equals 0. We basically get 1 over negative 1. So y-intercept would be at y equals negative 1. Right? Now we know our y-intercept. And the other half has no intersections, just simply smooth curve like that, joining positive infinity and positive infinity, as well as negative infinity and negative infinity to the left-hand side from vertical asymptote. So now we can see that the range is truly all rational numbers except for y never equals 0, because there is no x that would give us nominator equal to 0. Okay. Any questions on how to sketch rational functions? On how to analyze them? Okay, I treat it as no questions. So moving on, please do this example on your own. Copy this table to your textbooks, copybooks. You have now 10 to 15 minutes to do this exercise, this example. And then I'll ask one of you to fill out the table of values and we'll discuss it together, okay? Any questions? Did you understand the assignment? Okay, so take your time. Okay, guys, how is going? Any progress? Okay, guys. Let's make a 15-minute break now. We're 46 minutes into the class. Please take your time to finish this example, and after the break, I'll ask one of you to fill out this table with your answer, okay? Okay, guys, I'm back. So I can see Hala posted her answer. So, Safa, would you mind fill out the table for us so we can discuss your solution?
I haven't finished yet.
Okay, then anybody finished? Okay, guys, so take 5 more minutes to finish your solution and we'll discuss it. Okay, guys, I believe it's time to move on. So what about now, Safa? Are you done?
No, I think I'm getting lost. Sorry.
Okay, no problem. So let me describe this example for you. So we are working with function f of x 2 over x plus 5, right? Basically gonna go step by step. Domain are all values that x can take. We remember that denominator cannot be equal to 0. So we're gonna get x plus 5 does not equals to 0. Therefore, x does not equals -5. We can make a conclusion that our domain is such that x er excluding x does not equal -5. Okay? We can make a conclusion that we're going to have vertical asymptote x equals -5. 5. Let's move a little lower. Okay. We'll sketch the graph afterwards. Describe how function behaves near vertical asymptote. In order to do so, what we do, we approach x equals -5 from negative side. It can be also denoted as, you see a little minus sign in top right corner. And we approach x from positive, x -5 from positive side, from right hand side. So if we approach x from negative side, -5, we're gonna have -5.1, for example, right? Substituting that into our function would give us 2 divided by a very small negative number, which tells us that it's gonna be negative infinity to the left hand side from -5. And it would be positive infinity from the positive side. Now, we have to describe the end behavior. Yeah, so here, for example, let's fill out this table. Here we take x from the negative side, we take it -5.001 f of x negative infinity. From positive side, -4.0, oh, -4.999 f of x travels to positive infinity. Okay. Well, if we describe the end behavior for x travels to infinity, we're gonna see that function travels to 0, right? As well as if we travel to negative infinity, we're gonna get same travels to 0, but from the other side. For positive infinity, it travels from positive side to 0. From negative infinity, it travels to negative side from 0. We can make a conclusion that the line y equals 0 is a horizontal asymptote for us. So for example, we can take some really big number like 100 and then like 10,000, here -100, -10,000, And you're gonna see how basically we're approaching this 0 from one or the other side. From positive side, we would get something like 0.002, then we're gonna get 0.000002. You see, we're getting to the 0 from positive side. On the other hand, we would approach 0 from negative side. Okay. So we have conclusion that we have a horizontal asymptote. In order to sketch a proper graph, we also have to find y-intercepts. How to do it? Substitute x for 0. When x equals 0, f of x equals 2/5. This would be our y-intercept. Keep in mind that this function has no x-intercept because y does not equals 0. This is our horizontal asymptote. So what we're gonna do, we're gonna sketch the coordinate axis. Y and x. Vertical asymptote when x is -5 here is going to be our vertical asymptote. Horizontal asymptote is when x or y equals 0. Y equals 0 is horizontal asymptote. Use the green color for it. We know as x approaches positive infinity here, y travels to 0 from positive side, so from top of the x-axis. On the other hand, from negative infinity would approach here. Then around -5, how do we describe the behavior? From the left-hand side, negative infinity. From the right-hand side, positive infinity. So we can make a conclusion. Also, we know the y-intercept, 2/5. Let's say somewhere here, 2/5. So the graph passes through this point. So from left-hand side comes from negative infinity of x close to the x-axis, then bends like this, not crossing the vertical asymptote. Not crossing the vertical asymptote. And from the right-hand side comes from positive infinity and travels to positive infinity in x-axis. Okay, as such. So this is our rough sketch of the graph. Does anybody else have any questions about this? Or is it clear now? Safa, Mohammed, any questions? Rana, Ahmad? So when we talk about chart, what it gives us? Basically, here, this top part, I just skipped one step. What we do, we see how value of the function changes the closer we get to -5. -5.001, -5.0001. I just substituted negative infinity and positive infinity here because that's how we characterize it, because theoretically we get as close as possible to -5. So it will give us this behavior, infinite behavior. In reality, you're gonna get some very huge negative number here and some huge positive number here. If you get huge negative number, means negative infinity. If you get huge positive number, positive infinity. Then here, what we'll do, again, we approach x to positive infinity on this end, and we approach x to negative infinity on this end. We just take some numbers that we can calculate. The bigger the number, the better, the closer approximation would be. On the left-hand side, you can see that we approach 0 from positive side, so number is positive. On this end, we can see that we approach 0 from negative side, so the number is negative. Okay? Any questions on this example now? Safa, is that clear now?
Yeah, I think so.
Okay, great. What else do we have here? So what could you say about range of this function? Range of this function would be limited with its horizontal asymptote. So y does not equals 0. So range would be range equals x y e r excluding y does not equals 0. This is our restriction. We don't have any x-intercepts in this scenario. So to summarize the characteristics of the given the rational function, we see that it has vertical and horizontal asymptote, as well as restrictions on its range and domain. And what else? We know the end behavior of this function, as well as y-intercepts of this function. These are main characteristics that we can discover. Okay, if you don't against it, I'm gonna clear the desk. We're gonna move on to the reciprocal of quadratic function now, because now we looked at example with linear function, right? What about the reciprocal of quadratic function? So the rational functions are written in the form g of x, p of x over q of x, as I've said before, where p of x and q of x are both polynomial function, and denominator, which is q of x, does not equals to 0. Now we are making basically reciprocal more complicated than it used to be before. Instead of linear function, we use quadratic function now. Q of x does not equals to 0. That's important to remember for any reciprocal function. If y equals f of x is a quadratic function, then reciprocal of it has the form g of x equals 1 over f of x. Or g of x equals 1 over ax squared plus bx plus c. Okay, this is a general example. If we say that if our quadratic function is y equals f of x, then its reciprocal would be q of x, 1 over f of x. Basically, reciprocal of any function is 1 divided by this function. This is the quadratic form in denominator for g of x. And considering this function, I'll give an example, g of x equals 4 over x squared plus 2x minus 8 with minus sign in front of it. Let's go step by step. Let's state the domain of this function. Does anybody willing to do it? Mohammed Halil, you said you did it in a grade 11. Would you like to try answer this question? Mohammed, unmute yourself, please. Unmute yourself and please give an answer. What is the domain of this function? I can't hear you. Mohammed, I'm still waiting for you. Are you Googling what domain is? Mohammed, please don't stop the class.
Oh, excuse me, I'm just trying to figure it out. Just give me 1 second.
Okay, Mohammed, I cannot wait any longer. So the domain is the values that X could take. X, in this particular case, could take all the values except for those that make the denominator equal to 0. Okay? So we say that x squared plus 2x minus 8 does not equals to 0. So in order to find the limitations on the domain, we have to find when does the denominator equals 0. Okay? How can we do it? We should solve this quadratic function. I believe you know your methods on how to solve the quadratic functions, right? You know your methods. Does anybody knows the answer? What values of x would give us 0 in this case? I prefer discriminant method, where we calculate b squared minus 4ac, which equals, in this case, b is 2, so it's 4 plus, because we have minus here, 4ac, 4 times 8 is 32. 36. Now we need to find the x1 and 2, which will be minus b plus minus square root of discriminant divided by 2a. If I remember right, you can correct if I'm wrong. So negative b would be negative 2 plus minus square root of 36 plus minus 6 divided by 2a. 2 my negative 2 plus 6 would be 4 over 2, and negative 2 minus 6 would be minus 8 over 2, which gives us 1 root 2 and the other root negative 4. Mohammed, unfortunately, you're wrong. Maybe you can prove that I'm wrong, but I found these other two roots, 2 and negative 4. So the domain of this given function would be d equals x e r slash excluding x does not equals 2 and negative 4. So comparing it to previous example, when we work with linear function, we see that we have now two vertical asymptotes, 2 and negative 4, right? 2 and negative 4, two vertical asymptotes. Find the x and y intercepts. So we can see that there is no x-intercepts because this function never equals to 0. But y-intercepts there are when x equals 0, f of x equals negative 4 over negative 8, which is 1 over 2. Right? And vertical asymptotes, vertical asymptotes in these particular examples are x equals 2 and x equals negative 4. Describe the behavior of the function near the vertical asymptotes. So we have to look into values of x to the left and right hand side from 2, and to the left and right hand side from -4. When x equals 2 from the positive side, y equals, we're gonna see, for example, 2.1, 2.1. Does anybody can calculate it? I'll open my calculator for convenience. So 2.1 times 2.1, it's 4.41, plus 2 times 2, plus 4.2. Oh, divided by 4.2 plus 4.2. It will be 8.61 minus 8. So I'm gonna get basically -4 divided by 0.61. So if I get even closer to x2 from the positive side, I would get negative number divided by extremely small positive number, which means it will give me negative infinity to the right hand side from 2, which means from the other side we would have positive infinity most likely, because here we would have extremely small negative number, and negative number divided by negative number gives us negative, extremely small number. Extremely, oh, sorry, will give us extremely big positive number, which leads us to conclusion that it's going to be positive infinity. Pretty much the same for -4. We substitute x equals -4 from positive side, which gives us y equals -4 divided by -4 divided by, let's say, if x equals something like 3.99, 3.9 times 3.9 is 15.21 plus 15.1 plus some negative number minus 8. What is it gonna be? This gonna be small positive number. So -4 divided by small positive number would give us like zero. Imagine if it's like 0.0 something. So what we're gonna get is negative infinity to the right hand side, and to the left hand side from -4 we'll have positive infinity. If we were to sketch this function, right now we have pretty much information in order to do that. X, y. We know that we have no x-intercept, but we have y-intercept, which is 1/2. 1/2. We have two vertical asymptotes, -4 and 2. Right? Using that, we also look at our behavior of the function near the vertical asymptote. From positive side to 2, it will be negative infinity, so here. From negative side, it will be positive infinity, so here. And for -4, from positive side, it would be negative infinity, so here. From negative side, it will be here. We also have to define horizontal asymptotes prior to graphing this function. And how we do it, we travel x to positive and negative infinity. If we travel x to positive infinity, you imagine what would happen to this number. It would be incredibly big positive number. But we have negative in front of it, which means we'll approach 0 from below, from negative side, so from here. And when we go to negative infinity, realistically, you can see that we also have positive number, negative number. So we're gonna approach 0 from this side. Right? So I think I made a mistake here when finding behavior around -4. I believe it's going to be positive infinity to the right-hand side and negative infinity to the left-hand side. So that this, we're going to have it here, and this is here. So what's happening, that to the left-hand side from -4, we're going to have something like this. Here, between those two values, we're going to have our parabola like this, passing through 1/2. And to the right-hand side, we're going to have this. Look how beautiful this graph looks like. It looks like 3 curves separated by 2 vertical asymptote and by 1 horizontal asymptote y equals 0. Is there any questions on how I did this? It depends, but most likely on tests you won't be allowed to use graphical calculator to find x and y intercept, because in order to find x and y intercept, what you have to do, y intercept, first of all, it's simply x equals to 0. That's how to find y intercept. So it's pretty easy. You just substitute 0 in your function and many of the terms will turn into 0, right? And if you need to find the x-intercept, you just need to solve when the function equals 0, when y equals 0. This is not the purpose of graphical calculator, it's your own skill of solving quadratic functions for 0. If you don't have any questions, I'll scroll down a little bit. So we find the horizontal asymptote. You see here, next step would be for you to describe the end behavior. We did it by looking into positive and negative infinity. We sketched the graph. We found the intervals of increase and decrease by just looking at the graph that we sketched. You can see that the function is constantly decreasing to the left-hand side from the -4. It's decreasing from -4 to 0 and from 0 to 2 it's increasing, and then from 2 to positive infinity it's decreasing. So how would you write it down? Negative infinity to negative 4 decreasing, then negative 4 not including, because negative 4 is a vertical asymptote, negative 4 to 0 decreasing, then 0 to 2 increasing, then from 2 to positive infinity, function is increasing again. So first two intervals decreasing, then second two intervals increasing. Any questions on that, how I did this one? I will keep it on the screens. Try to do my best. Just gonna shrink it a little bit. Okay. And now it's your time to do a little work. Example 2. Given the graph of a quadratic function, draw its reciprocal function. Exactly the same way we did. So for example, here you have quadratic function. First of all, you have to find how it looks like. So it's going to be x squared plus x plus c bx ax squared. You have to find a, b, and c. This is what you were supposed to learn in the previous classes, and as well as grade 11, maybe. So what you have to do is to draw its reciprocal function. Please, we're gonna take a break. You can start doing this exercise right now, example number 2. Start with the graph number 1. That would be at least take off point for us now. Yes, Mohammed. What is your question, Mohammed? Reciprocal means if you have function like x squared plus x plus c, the reciprocal of this function would be 1 divided by x squared plus x plus c. This is the definition of reciprocal function. When you divide 1 by this function. Okay, basically gives you inverse relationship. Okay, 15 minutes from now, you take your time to do example number 2, first picture, and I'm gonna denote you the vertex. It has coordinates x equals 3 and y equals -2. No. That's the inverse relationship. Yeah, I made a verbal mistake. That's what you're talking about, is the inverse relationship. But reciprocal function is when you divide 1 by this function. If I'm not mistaken, you can fix me.